Okay, what is angular momentum? Now, there's a lot of stuff going on here, so I'm just going to give you an introduction to the main concepts, and we can work some problems later and do a whole bunch of cool stuff because there is a lot of really cool stuff to do. But let's get started. Okay, I'm going to start with the momentum principle, just as a review. So if I have some object, this yellow ball, whatever it is, and I apply a force on it, a net force, there's only one force on it. What does that force do? It changes the momentum. The momentum, not the angular momentum. So momentum, we use the vector p, and it's equal to the mass times the velocity vector. As long as it's not moving near the speed of light, this works really well. Okay, so that's momentum principle. Now imagine the following situation. I have these two balls, and they're connected by a spring, and it's out in the middle of space, so there's no other forces acting on it. And so both the balls can move, and we can model this situation because all I have to do is calculate the spring force on the yellow ball, which is the same spring force on the red ball, and then just let it go, right? And then update the momentum, update the position, and here is what that looks like. Is it? Okay, actually, that stopped. Well, you get it. That it's moving along. So I just want to point out that this is actually a Python program, and I'll include the link down below. And I'm pointing. I don't know if you can see me, but I'm actually pointing down below. Doesn't really mean anything. Okay, but it's not too difficult to calculate this. I mean, you can make the spring look nice and all that stuff, but all I'm doing is using the positions of the two masses to calculate the spring force based on how much it's stretched or compressed, and using those forces to change the momentums of the two balls, and I can do it. There's no angular momentum in that calculation. It's just Python. Now with that, I can then plot the momentum. So this is just, momentum's a vector. So I can't plot a vector, but I can plot the x component of the momentum. So here is the momentum of the two balls as they move around. The blue curve is one of the balls, the red curve is the other ball, and then the sum of the two momentums is the black line, which is right there at 0. So that's cool. Why does that work? So the total momentum is constant, and so we say it's a conserved quantity. If I look at ball A and I use the momentum principle over some short time interval, I can say the change in momentum of A is the force on A exerted by B, because B is pushing on it with a spring, times the time interval. I can do the same thing for ball B. The change in momentum of ball B is FA on B times delta T. But those two forces are the same force pairs. So the force of B on A is the negative of force A on B. And so if I use that, I get the change in momentums are opposite, equal and opposite, and the total change in momentum is 0. So momentum is something that is conserved in this situation because there's no external forces on the system. That's why we like momentum. Here's another conserved quantity. We can look at the energy. So I have, first of all, I can define kinetic energy is 1/2 mass times velocity squared. It's a scalar, so I don't have to worry about components. I can find the spring potential energy of the system as 1/2 k, the spring constant, times s, the stretch squared. And then I can calculate the total energy as the kinetic energy of ball A plus the kinetic energy of ball B plus the potential energy of the ball's system, and that should be a constant. So here I plotted that same thing. This is the same calculation using the momentum principle. So the blue and the red lines are the kinetic energies, and the green line is the potential energy of the spring. And if you add that all up, you get the black line, and you can see it's almost a little less than 0.18, but it's constant. So energy is a conserved quantity. So we like energy, we like momentum, they're conserved quantities. What about something else? What if I just did the angular velocity? So now in order to get a nice graph like this, I actually changed it. Does not the same animation. I started off with the balls so that they're spinning fast, and then they stretch out and they slow down. But you can see if I just look at angular velocity of the system, it's not constant. Momentum of the system is constant, the energy of the system is constant, but not the angular velocity. But there is something I can do that is constant, and that's angular momentum. If I define angular momentum using the vector L as the cross product of the position and the momentum, that's angular momentum. So that is a cross product, a vector product. So we're going to have to talk about that. That's a little bit different. And then the other thing is this R vector is from some point. I have to pick a point about which to calculate the angular momentum. So if I move a different point, I'd have a different value. but angular momentum is also a vector. So let's look at the cross product. So suppose I have vectors b and c, and I take b cross c to give me vector A. The vector A has to be perpendicular to both vector B and vector C. So this makes it really difficult to visualize because you have to be in 3 dimensions. The only way vector A can be perpendicular to B and vector C is to be in another plane than B and C. So we use the right, there's actually two, if I have two non-parallel vectors B and C, there's actually 2 vectors that are perpendicular to both. And I'm not going to go into all the details because it's only partially important right now. And I use the right-hand rule to determine which one it is. So here's an example. Here's the red vector A is yellow. Wait, did I do this right? Yeah, okay. The yellow A cross red B gives me, in another dimension, A cross B, which I call C. And this is a Python program. I didn't want to actually manipulate it around, but we do get a vector value. Now, if you want to find the magnitude of that resultant, it's the magnitude of vector B times the magnitude of vector C times the sine of the angle between those two. So if the two vectors are 90 degrees, sine of 90 is 1. If they're parallel, then theta would be 0, and the cross product would be 0. Okay, which is good because then there's like an infinite number of vectors that they're parallel, they're perpendicular to both. Okay, here's another way to calculate the cross product. If I have vector B and I know the components, bx, by, bz, and I know vector C's components, cx, cy, cz, then the resultant vector would be this crazy formula, which I don't want to get into right now, but I just want you to know that you can indeed calculate it based on the products of the components at the end. But wait. You can also do this in Python, just a little commercial for Python or GlowScript vPython. You can't do this in normal Python. If I define these vectors B and C as vector objects in GlowScript, there is the cross function built into GlowScript. So I can say cross BC, and I print it out and I get the answer. There you can see it. Also, I'd like to point out that B cross C is not the same thing as C cross B. You see, you get negative values of each other. So you got to be careful. You can't just switch them up. What if I wanted to calculate the angular momentum for a simple case like this? Here's a ball traveling in a circle. And in fact, I made this as a Python program that's actually a spring pulling it. So I don't have to I can use normal momentum principle to calculate this situation. And I can calculate the angular momentum. So here is some instant in time. I could find the vector position r, I can find the vector momentum p, and I could take r cross p. And at some later time, r changes and p changes, but r cross p is constant. So this would be a constant angular momentum. And in fact, the angular momentum vector, I should have shown this, is actually pointing out of the screen. Okay, because that would be perpendicular to both r and p. Let's go back, though, to the more complicated case of the 2 balls connected by a spring. So here are those 2 balls again. And if I use the center of mass, these are not the same mass balls. Okay, they're different masses. If I use the center of mass to calculate the angular momentum, then both of these balls have constant angular momentum. So r changes. The r values for each of these changes, but the velocity changes too. The momentum changes. And r cross p is actually constant from the center mass. So here you have the blue and the red are the 2 angular momentums, and the green is the total angular momentum, and it's constant. Now, again, angular momentum is a vector. So I actually have to plot a component of the vector. This is the z component of the momentum. It's not everything. But in fact, the other components are boring, so you're cool. What if I use a different point to calculate the angular momentum? So here's a point not at the center of mass. And if I want to calculate the angular momentum, it's not so trivial, right? Because now R1 and P1 change, R2 and P2 change, and I get these curved plots. The angular momentum of P2 is not constant, and the angular momentum of P1 is not, ball 1 is not constant. But if I add those 2 together, you can see I get the green curve of the z component of the total angular momentum is constant. Okay, so here we have the important thing. Angular momentum is conserved in this situation. And I'll show you a case where it's not conserved, but in this situation, angular momentum is conserved, and it doesn't even matter what point you pick. So that's why we like angular momentum. It's a conserved quantity. What if I have something like this? This is 3 masses connected by springs, so it's a lot more complicated object. And in fact, you can see they're jiggling around a little bit because I didn't apply the correct initial conditions. But again, I'm just using forces and momentum to model this, and then I'm calculating the angular momentum of the objects, and this is what I get. So the angular momentums are not constant for the 3 balls. So you can see those curves, they jiggle all over the place. But what is constant? The black curve. You see it at 0.01. So the angular momentum of the system is indeed constant. The angular momentum, the z component. So there you go. So even with 3 masses, I get conserved angular momentum. I know these are not popular anymore, but here's a fidget spinner. And I'm so glad that I actually took this video of a fidget spinner a long time ago, and now I can reuse it. Yay. Okay, so what about something like this? This fidget spinner is not 3 masses. It's, 10 to the 24th masses, 10, something like that, right? There's a ton of atoms in this fidget spinner. What if I just take 4 of those atoms and I want to calculate the angular momentum about the center of the fidget spinner? Well, I can find the position for each mass, and I could find the momentum for each mass, and I could do L equals R cross P for each mass. This is for each mass. And then I can add them up and do the whole thing. Every single mass has an angular momentum, and add up all of them, and I'd get the total angular momentum. But what if I write the angular momentum for one mass? I factor out the mass out of the momentum. So I get mass times R cross V. And then I can use the definition of angular velocity. This one's a little bit harder to see. But if I have an object moving in a circle, the angular velocity vector is defined like this. This is the vector definition of the angular velocity. And so it is actually in the axis of rotation using the right-hand rule. Now if I substitute this in, I get the angular momentum for one particle in this would be mr squared times omega. But all the particles have the same angular velocity. So I can actually put that mr squared into this for all the particles. Now this is for all the particles as some constant I times the angular velocity vector, where I is a sum of mass times radius squared, position squared, for all the masses in the object. And we call this the moment of inertia. And this is for a rigid body. So a rigid body means that the masses stay in a relative position to all the other masses in that object. It's rigid. Not like Jello. Jello's not rigid, right? This has to be rigid. Now, I'm going to talk about this in a little bit, but this is only for fixed axis of rotation. If I let this rotate freely, it doesn't work. I have to say it's rotating about this axis, and that can't change. So you can do this for a whole bunch of different objects. I could take something like this. This is a rod, and I'm going to rotate it about that axis that passes through the red dot, and I could break the rod into tiny little pieces, and then take the limit as the piece size goes to 0, and it becomes an integral, and I can integrate to find the moment of inertia about that axis. And so in this case, if the rod has a length L and a mass m, you could derive this, and I'll do it for you later. It'd be 1/12 ml squared. But what if I take that same rod and rotate it about the end down here? It's going to have a different moment of inertia because the mass is distributed differently. So different parts will be moving at different momentums compared to that rotation, and I'd get 1/3 ml squared. So it's a higher moment of inertia. What if I have a disk? This is a disk. The moment of inertia is 1/2 mr squared. A hoop has a moment of inertia of just mr squared. And again, I can derive all these things. Okay, but that's just that dealing with rigid objects. Now let's talk about the torque, because the question was earlier, how do you change the angular momentum? Well, torque is the answer. So just like forces change momentum, torque changes angular momentum. So torque is like a rotational force. And suppose I have this stick and I want to calculate the torque due to some force about that point O down there where the red dot is, then the torque would be the position from the dot to where the force is applied, R, cross F, the actual force. And again, we have the cross product. So you could calculate the magnitude of this. Again, it's just from the magnitude of the cross product r f sine theta, where theta is the angle between f and r. You can also, this is another useful form, the magnitude of the torque would be r perpendicular. I should have drawn this, but if you draw a line from point O to a line where the force is, but you make those two perpendicular, then r perpendicular times the force is the torque magnitude. Or you could do it the same way. You could say the force perpendicular to r, and that would be the torque. And then there you go. Here's the angular momentum principle. So torque, the net torque on an object changes the angular momentum with respect to time. It looks just like the momentum principle, but instead of force, I have torque. Instead of momentum, I have angular momentum. So that's kind of cool, right? Okay, now for some warnings. I told you that the moment of inertia is not so simple as a single value. That was only for a fixed axis of rotation. Check out this guy in Skylab. This is from the original spacecraft that was in orbit, and he is spinning around, and his angular velocity, I mean, I don't know if you'd call his angular velocity constant, right? Because he changes the way he rotates, which is really kind of cool. This is an animation of a person flipping. I did that on the left too. And the key here is the red arrow represents the angular velocity vector. It's not constant, but the yellow arrow is constant. But angular velocity and angular momentum do not have to be in the same direction. And that's because the moment of inertia should actually be a tensor. Okay, and this is how you'd calculate. But I want to talk about that just to show you that it actually can get more complicated. And we will do more complicated angular momentum stuff later. But let's end with the key ideas. 1, momentum and energy are conserved in some cases. If you have a closed system with no external forces or no external energy inputs, then the total energy, the total momentum would be constant. It's conserved. The same is true for angular momentum. Angular momentum is conserved when there's no external torques. Okay, so I showed you a bunch of cases where we did the angular momentum by looking at the momentum of a point mass, or 2-point masses, or 3-point masses. And so you could say, well, what the heck? Why not just does angular momentum even matter? Just use momentum. And essentially you're true. That's true. Okay. It's easier if I have a rigid object. I don't want to do 10 to the 24th calculations to do moment and use momentum, when I could use one calculation with the moment of inertia. But angular momentum isn't just a shortcut. If you look at quantum mechanics, it turns out that atoms, we can model atoms as having quantized angular momentum. Whether they're actually spinning or not, it doesn't really matter, but we can use the same idea in quantum mechanics when we talk about orbitals and things like that. So there is a more fundamental use of angular momentum. It's not just a shortcut. But the best part to do is just do a whole bunch of problems. So we should do some angular momentum problems. And I will do that later. But there you go. That's your introduction to angular momentum.